Hello and welcome to lecture 5 in our series Transformation Semigroups and Applications. I am Imam, a lecturer at the Department of Mathematics, Ahmad Bello University, Zaria. In this lecture, we are going to talk about kernel, standard orbit, and acyclic orbit of a finite full transformation. So we define the concept of a kernel of an orbit. Now let omega be an orbit of alpha in Tn, Tn being the full transformation semigroup. And suppose that the orbit is not entirely contained in the image of alpha. In the last lecture, we look at the situation where the orbit is contained entirely in the image set of alpha. And in that case, we show that the orbit is cycle. It's a cycle. It's either a cyclic orbit or a trivial orbit. Now we are looking at the situation where the orbit is not necessarily or is not contained entirely in the image of alpha. And then with this assumption, if we choose x, a non-image point from the orbit, then the sequence x alpha square will continue indefinitely. But this sequence is a sequence of terms coming from the orbit. Since x is an element of the orbit, each member of the sequence here is an element of the orbit. And since we are in a finite situation, the sequence must contain repetitions. Let xm be the first entry of the sequence to repeat. Here we observe that m must be greater or equal to 1 because the first entry to repeat in the sequence cannot be x here, because x is not in the image of alpha. Since x is not an image point, you can see that in the sequence, apart from the first term, which is x, every other term of the sequence is an image point. So therefore, the first term of the sequence cannot be the first entry to repeat. And let us assume that x alpha mr is the first repetition of the entry x alpha m. Then with this in mind, we define the notion of kernel of an orbit. For each orbit omega of alpha, we define kernel of omega to be the set k of omega equal to x alpha square up to x alpha r minus m. This is in the situation where the orbit is contained entirely in the image set. So this is the situation we look at in our lecture 4. And in this case, the orbit is equal to the kernel, because we saw last time that if omega is contained in the image, then omega can be written as x alpha square up to x alpha r minus 1. And in the other situation where the orbit is not contained entirely in the image set, we take the kernel of the orbit to be equal to x alpha m plus 1 up to x alpha m plus r minus 1. But then we assume that x alpha m is the first entry of this sequence to repeat, and the first repetition occur at x alpha m plus r. So therefore x alpha m is equal to x alpha m plus 1, and then the sequence, this situation will continue to repeat in a cycle. So this kernel of the orbit is nothing but a cycle, that is the cyclic part of this particular sequence. Because if you continue this sequence at xm, if you repeat as xm x alpha m plus r, the sequence will continue to repeat in a cycle. So the distinct element of the cyclic portion of the sequence that repeat is what we call the kernel of the orbit. You can prove as an exercise that this definition of the kernel is actually well defined, in the sense that if you pick a different element of the orbit and define the kernel, for example, if we take a different y from the orbit, we have seen it last time that it doesn't matter which point of the orbit you pick. If the orbit is contained in the image, whatever point of the orbit you pick, this r here is unique, and you can have x alpha square up to this. The set of elements would still remain to be the same because the entire orbit is equal to this set of distinct element here. So likewise, in this situation where the orbit is not entirely contained in the image of alpha, you will be able to show that the definition of the kernel is not changing by the choice of the element x not coming from the image of alpha. So you can prove it as an exercise here. And then with this definition at hand of the kernel of an orbit, we now proceed to introduce what we call standard and acyclic orbit. So it is clear, first of all, that for a cyclic and trivial orbit, the kernel of the orbit is the entirety of the orbit itself. But if the orbit is not cyclic, then the kernel is contained properly in the orbit. And so, for such an orbit that is not contained entirely in the image set of alpha, or where the kernel is contained entirely in the orbit, we say that the orbit is a standard orbit if the size of the kernel is strictly greater than 1. And the orbit is called acyclic orbit if the cardinality of this kernel is equal to 1. Now we look at some properties of this kernel of the orbit. For example, for any given orbit of alpha in Tn, with alpha not contained in the image set. So in other words, we are saying this orbit is either standard or acyclic. Then if you consider a standard or acyclic orbit, then for every y in the orbit, there will always exist an integer, a non-negative integer t, such that on the application of alpha on y, t times, you will get into the kernel. So if you keep on applying alpha on y, a certain number of time, you will eventually arrive at the kernel. This is the content of this particular observation here. And then we can prove it easily, because by the very definition of the relation tilde that gave rise to the orbit, since x and y are related, then it means y alpha u is equal to x alpha v for some u v greater or equal to 0 for some non-negative integers u and v. If v is greater or equal to m, then there is nothing to prove, because any integral power of alpha applied to x that is bigger or equal to m will eventually be a member of the kernel. So therefore, that y alpha v alpha u will definitely be in the kernel, and so you can just take u to be equal to t in the lemma, in the statement of the lemma. While if v is less than m, then we can easily see that y alpha u plus m minus b, and now here m minus b is a positive integer because v is strictly less than m. So this can be written as this using indices, from which up here we have y alpha u to be equal to x alpha v, and then when we use indices again to add the powers, we arrive at x alpha m, which is already a member of the kernel of omega. And so therefore we eventually arrive into the kernel on applying alpha on y a certain number of time, this number of time. So we take this to be our t as in the statement of the lemma. Now the next observation is to say that if one consider an orbit of an alpha Tn in Tn with kernel size equal to r, then for every y inside the kernel, if you apply alpha r times on that particular y, you will still arrive at y. So which means you can start with every member of the kernel and keep on applying alpha, and you will eventually remain into the cycle. So this is, and conversely, if y has the property that you come back to y after a certain number of application of y of alpha on y, then even when you apply alpha on y r times, you will still come back to y, and the entire kernel of the orbit can be written as y alpha square up to y alpha r minus 1. Namely, the kernel of the orbit is just a cycle that can be formed by using any element of the kernel. So this is our second observation. Then we can prove it easily here. You can see that by the very definition of the orbit, of the kernel of the orbit, we have that for some x in omega and some m greater or equal to 0, kernel of the orbit is this. This is how we define the kernel of the orbit, with this particular relation holding. Hence, if y is just a result of an integral application of integral power of y of alpha on x, then y is already in the kernel. Because y is in the kernel, so y is equal to one of this element for some I. But then it means y alpha r will be equal to x alpha m plus I plus r, because y is equal to x alpha m plus I, and then plus r using indices, and then you have x alpha m plus I, because r is actually the size of this orbit. So if you apply alpha r times on any member of this particular element of the kernel, you will still come back to the element of the kernel. So this is equal to this, but which is also equal to y. So therefore, the requirement of the theorem is, or lemma, is satisfied. And in the converse, if we also assume that y alpha k is equal to y for any element y coming from the orbit, then we can see that y alpha k, y alpha 2k, if you keep on applying alpha on y, multiple of k times, you keep on arriving at y. And so this, by the lemma, by the first observation we had, then it means there exists, by the very first observation we have, we can arrive into the kernel starting from y. So starting from y, we arrive into the kernel. And so therefore, if we choose I such that I times k is already bigger than t, then we can see that y is equal to y alpha ik will eventually be in the kernel, because there has to be a multiple of k that is greater than this particular t. So an every multiple of k is coming back into y. So therefore we will arrive into the kernel in that way. And so it then follows, because once you are in the kernel, if you apply r times alpha on it, you would still come back to the element. And so therefore it follows that this is what the kernel is. So this is the property. So in order to look at a next property of the kernel of the orbit, we introduce this concept, the concept of set of eventual pre-images. For example, here we are saying if you pick an orbit of the kernel and a point of the orbit, then we introduce a notation p alpha minus n. This is just a notation to denote the set of all x such that x alpha I is equal to p, something which I call set of eventual images. That is an element that if you apply alpha on it a number of times, you eventually arrive at p. So this is the notation for this particular set. So if we understand what this set is, then we can see immediately that p will belong to the kernel if and only if p belongs to the set of eventual images, set of its eventual images. And then, so with this property, we can have this observation, that is, if we take omega to be an orbit, then p is in the kernel if and only if the set of eventual images of p is equal to the entire orbit. This is not difficult to see, because if we suppose p is in the kernel, then by the lemma 4, the last observation, the orbit is p alpha square up to p alpha r minus 1. But then this will get us to p alpha r equal to p.